Thanks.
Yeah, thank you.
Go ahead and get started.
All right, so let's continue our discussion. And at the end of last lecture, we kind of introduced the Gottesman-Kittel-Preskill code, which is a coding scheme that uses a single bosonic mode to encode qubits by using superpositions of different coherent states. And the choice of this coherent states is that they will be co-eigenstates of these stabilizers correspond to displacement along the position or momentum direction by 2 times the square root of pi. Now why that's actually a good choice is because you can think geometrically that you make a displacement along position or along momentum. And then if you do this operation like along position, momentum, backwards in position, backwards in momentum, you'll enclose an area. And if that area is integer multiple of 2 pi, then the operators of the displacement along position and momentum, they will commute with each other. Okay, so now one choice is actually to have the enclosed area to be 4 pi. And why I need 4 pi is because that actually allows us to encode 1 logical qubit. The way to see that we can encode 1 logical qubit is because first we agree that the stabilizer operators, they commute with each other, and we can try to find a co-eigenstates with eigenvalue +1 for the stabilizer operators SZ and SX. Now the trick to introduce a logical operator is to take a square root of the stabilizer operator. Okay, because we know it's a qubit. If it's a logical, is equal to ±1. When we square it, it will guarantee to be +1 for polys. And then if we have a stabilizer, we can take a square root. Literally take a square root. And here just say make a half of that displacement. Okay, so now once I make that definition, one can see if I can find the matching colors for the, let's say, this is the stabilizers for S. Well, I wonder which is SZ, which is SX. That's SZ, and that's SX. And the logical Z operator is only half of the stabilizer. This is a logical Z, and that's logical X. So the area associated with the stabilizer, this is 4 pi, which is 2 times 2 pi. Now, since this, the logical operator, the area enclosed is actually a quarter of the big area, which is pi. Okay, so the area, if it's pi, then these 2 operators, they actually become anti-commuting with each other. So that allows us to define a logical operator. However, what about the commutation relation between this logical and this stabilizer? They commute with each other because actually they are the displacement along the same direction. What about this X logical and the stabilizer Z? When you carve out this area, for the green area, this is equal to 2 pi. So the logical actually commute with all the stabilizer operators, but only the logical operators, they anti-commute with each other. So this is a construction to encode E equal to 2 encoding. Now, once you see this pattern, you can say, I can give a more general encoding to encode a D-level system. I can have my SZ and SX, this area to be D times 2 pi. And I can define my logical to be the Dth root of the stabilizer, and similar, the X logical to be the Dth root of the X stabilizer. Then the area enclosed, this will be 2 pi over D. And that implies the commutation relation between the X and the Z. So it's X logical, Z logical. This will be something that's omega Z logical, X logical. And that omega is e to the 2 pi over D times I. So that's the commutation relation associated with a qubit with a D-level system. So now you see the pattern. That's basically if I make a this stabilizer to be like related to this square root of d with a displacement. My logical operator will be 1 over square root of d of the displacement. And that's a systematic way to encode d-level system for my harmonic oscillator for GKP code. All right. But here it's just the example for 2-level system, and we can get this anti-commutation relation. Yes?
The X operator are not sufficient.
Okay, it's fine because notice that generally for D-level systems, the X and Z, they don't have to be Hermitian operator, because what X and Z here refers to is more from the unitary perspective, that it implements the operation of doing X rotation or Z rotation by 180 degrees. Generally, this may not look to be unitary, but for that particular logical space, this operator will guarantee you get kind of like a real plus or 1 or minus 1 for the logical space. Yeah. So generally, it's not unitary. Yeah.
He's related to Hamiltonian.
Yeah, in some sense, there is kind of like a fractionalization in there, right? But here, the only fractionalization comes is that there is this like a geometric phase when you consider the commutation between these operators. And it's associated with a carved out area, which is because it's bosonic mode, there's sort of effective curvature in there. Yeah.
And also, if you think of it as from the condensed matter point of view, as having a Hamiltonian,
yeah,
like in the Tory code, two stabilizers, should I think of it as your Hamiltonian with an external field, acting SC and SX,
yeah,
stabilizers, or is that something? What's the Hamiltonian?
Okay, yeah, well, and that's a good question. That people also try to construct like Hamiltonians associated with the stabilizer, so that you will get some like ground states, which is associated with like the GKP, or maybe even come up with some dissipated engineer dissipation, which will stabilize these quantities. And if maybe just I can really give that. Yeah, maybe just with 1 minute, I will just give out what that the construction. Well, okay. Because one way to think of it is that you want to design a Hermitian operator as a function of S, Z, and X, so that the lowest energy states are these logical states. And I think that probably okay, it's not unique to write it, but I think that if you probably like takes the S, Z, SX minus 1 and sort of square it, it probably can give you something. But hopefully the good one will give you some like gap compared to other states, which that part I'm not sure that how to ensure that. Yeah, because the good thing about Tory code is that there is a gap that you can sort of guarantee it will converge to that quantity. And here it's a bit continuous. That's a part which, okay, I need to look it up if there's a good way to do that. Yeah. Yeah, well, maybe one way to do it is SZ plus 1 absolute value square or something like that. You can come up with a Hermitian operator for it. Yeah. Yeah, but I don't know whether or not it will be gapped for those cases. Yeah, because it's a continuous system, right? Yeah. Yeah. So yes. Yeah, maybe that will answer your question. Because so far I was just plotting kind of even the previous one is just about the projection of the code space. And now let's just maybe see what the logical states are, so that I will connect it to my logical operator. So notice that the logical Z correspond to displace along let's look at logical X because that go from 0 to 1, that displace along the position direction by square root of pi. So here are the logical 0, logical 1. And let's just look at those stripes which are associated with all red dots along the vertical direction. So those columns, you can think it as like the infinite squeezed vacuum, infinite squeezed states, and it's a superposition of those. And here you see the alternating red and the blue dots is actually because of the interference. Suppose you have to squeeze vacuum, you actually have a fringes associated similar to the cat fringes. So this actually corresponds to superposition of infinite squeeze states at an integer multiple of 2 times root pi. And for logical 1, it's a superposition of infinite squeeze states at odd integer multiple of root pi. So spatially, they sort of like always kind of like offset by the even and odd lattice sites. And now the logical X basically displaced from the kind of even sites to the odd sites along the X direction. And that's how you make this logical operation flip from logical 0 to logical 1 and backwards. Now, what about you make a superposition of these two? And the Wigner function, you can actually literally add up those things. This is the lattice you will get, which will be the logical plus. And you take 0 minus 1, that's the lattice you will get. And now if you look at the pattern on this plus lattice, you will see it's actually like a superposition of infinite squeeze states along the horizontal directions. And the logical plus, only those associated with the infinite squeeze states horizontally at the even integer multiple of pi, while the minus state is odd integer a multiple of pi. Okay, so that's consistent with the logical z operation, because the logical z just shift from even to odd, which goes from plus to minus or minus to plus. Yes.
Again, what's the blue color represent?
So this is a Wigner function. The red means positive, the blue means negative, and here you may see there's a sort of Gaussian envelope because we're plotting the finite energy GKP states. Okay, now if you want to think like this is a Wigner function, usually we can say integrate along the p direction, you actually get the marginal distribution along x, right? And here you will get spikes at even locations of x, and here you get the spikes at odd locations along the x of integer multiple of root pi. Okay, so basically like this is what the function will look like for the logical states, and consistent with the logical operators. All right, yeah. So now, as we said earlier, we can actually, if you have some like a random displacement, so you can think of it as a mixture of somebody tossing a coin to determine how much small displacement you do. And if the displacement is smaller than this lattice spacing, then basically measuring the stabilizers will tell you about the amount of the displacement in both position and momentum modulo square root of pi. And then you can use that information to displace the lattice back to the original sites so that you will restore the logical code word of the GKP code. Yes?
Actually displace these.
Yeah.
You don't actually get the other state. So
yeah, you need to make sure the Gaussian envelope is at a variance which should be much smaller than root pi, so that the tail of the Gaussian do not mess the quantum states up. Yeah.
What is the error that you incur? So if I apply a z in the plus state, like what?
Yes. So let's look at, this is a logical 0 state, and that's the position. And I can also show the logical 1 state. And the original spacing here is 2 root pi, and the spacing between the different logical word is square root of pi. Okay, so now if we make some random displacement, which has a, so suppose this peak gets kind of like under some like a random displacement with some like Gaussian profile. It has a variance or standard deviation of sigma. Then the question is the sigma, how many sigmas we are away to get to the square root of pi? And it better be larger than 3 or 4 sigmas, so that the tail will be very small, so that you will kind of not mix between the displacement from here or the possible displacement from the other states. So the requirement is sigma should be much less than square root of pi over 2, so that you don't mix with different states. Okay, and it actually, like once this is condition satisfied, then it's a Gaussian tail that will cause error which is kind of doubly exponentially suppressed. Yeah. Okay, so now I hope give you some intuition. Oh yes, question. Yeah. Yes. Okay, perfect. Yeah. So this is a part actually like some of the related to the recent development, because so far this is more like a purely theoretical. You can write down the states as the stabilizers, but if I don't do normalization, the state is unbounded, right? Basically, you cannot even write down a normalization of the state. Now, one way to actually overcome that issue is to introduce a finite energy GKP state. So let's say this is some of the logical states that we can define for the GKP states. And the way to define a finite energy GKP up to some normalization is to introduce this envelope function, e to the minus delta square a dagger a, which is, you can think it as the photon number introducing a thermal or Gaussian envelope, depending on whether you look at the photon number distribution, that will be an exponential distribution. In the phase space, it will be a Gaussian profile that you introduce. Multiply psi logical GKP. And then up to some normalization, that will be the finite energy Gottesman-Kittel-Presker code. The way you can see it will guarantee to be normalized is because if you look at the photon number distribution, it will actually have some like a kind of thermal-ish like distribution profile that helps to control the system. And here you may say that what's the average photon number? Which is roughly 1 over delta square. And delta is a parameter you can tune so that you will guarantee that the system will kind of like converge. And the inverse of delta, if you think in the phase space, that's a typical radius, which is associated with 1 over delta. That determines sort of the size of the GKP. All right. And practically, we'll see that when this is about 10, we can already get a very, very good GKP. I will show in a few slides. Okay, so that gives you the definition. But now you may see what are the stabilizers, because now previously we defined nice stabilizers. For example, SZ is e to the I 2 root pi ln x. Right. Hope. Yeah. So now what happened here is that we can define a modified stabilizer to be original stabilizer sandwiched by this operator. Okay, because what we know is original stabilizer, SC acting on the GKP is equal to +1 psi logical GKP. But now the state will be something like this. So what I can insert here is to insert e to the minus delta square n, e to the plus, and e to the minus delta square n, because these two multiply equal to 1. Okay, but I will group this part together and combine this with another e to the minus delta square away. So I'll define my new stabilizer to be e to the minus delta square n, the original stabilizer, e to the plus delta square n. And that gives me the effective new stabilizer. And this stabilizer, if you write it out, it will have a form which is e to the I 2 root pi, and then associated with the position displacement. And then there is an imaginary part associated with the momentum displacement, where the C delta is cos delta square, and S delta is a sinh delta square. Now takes the delta to be 0, this vanishes and this restores the original stabilizer. But when I have finite delta, this part is kind of like usually the Hermitian and the exponent, which are unitary for the stabilizer. But this part is actually anti-Hermitian. So that will actually give us some kind of Gaussian envelope-ish behavior. Okay. And experimentally, people developed the protocols to sort of implement such a stabilizer for both SX and SZ. That's what the kind of Michel Deville's group they come up with. And this is formulation is developed by like Steve Gervin's group. They actually find out that this will be the way to implement the stabilizer. So what happened is you start from some other states, you apply the stabilizers again and again, and it will actually push the system towards this logical GKP states. Okay, yes.
So now I guess your stabilizers are neither Hermitian nor unitary.
Yes.
So
yes.
Is that not a problem?
Well, what you want is that to have this quantity to be to help you to stabilize to that particular logical state with eigenvalue +1. Yeah. So I'll put another way is what you want to implement is some operator that effectively implementing some form like this. So experimentally, what's happening is the following: that we want to have a system with finite energy. However, once you measure the position and momentum like these operators, it does a horrible thing in the complementary quadrature, because it will have an infinite back action if you measure this really precisely. And that will cause a blow up in the energy. And that's why we actually need to do something to avoid that blow up of the energy. And that's why there is some non-Hermitian part in here. Okay, so yeah, maybe if you're interested, I would refer to this paper. Well,
it's really well written.
Yeah. And also before this, there was an experiment which the procedure was complicated, but this paper really clarifies why that's what's going on with the experiment. But nowadays, when people do the experiment, they actually just say, well, they don't even tune the parameter, they just do the machine learning to tune those parameters. So it does even another factor of 2 or 3 improvements as well. Yeah. Yes.
Can you explain it like back action, like things if I have
commuting
operators and there's no back action?
Yeah. So here the back action is actually related to, suppose you measure let's say the stabilizer Z, which let me just say tentatively say this is the operator that you measure. So you know some information about X. Okay. Yeah. So now suppose that your state is let's say it is a lattice which is like this. Suppose it's a momentum eigen, it's a squeeze state, which is along the Z direction, P. So suppose initially you have P equal to 0 state. Okay, so that definitely satisfies the condition that Sx acting on P equal to 0 is equal to P equal to 0, right? Because it has an even location at the momentum P, so that Sx will equal to 1. Now, what if I apply measurement associated with this operator with the outcome to be +1? So this operator and also Sx, they commute with each other. So the eigenstate of Sx will still remain as the eigenstate of Sx, while the Sz, if I suppose measure to be +1, now I will prepare a co-eigenstate of Sx and Sc both equal to +1, right? So that must be some GKP states. So initially I have a squeezed vacuum, but after measuring this with eigenvalue +1, what happened is it becomes a superposition of squeezed vacuum that actually prepares the logical plus state. And it localizes X into the position which are kind of some like lattice values. Yes.
you're saying that will also create back action, these echoes of the.
Exactly. So initially you have a squeezed vacuum, and after this measurement, if it's +1, you actually prepare a GKP state. Well, there's nothing wrong with that, but that's a back action, which introduces a big uncertainty in momentum P, because initially there is no uncertainty in momentum P, but now after this measurement, you have infinite uncertainty in momentum P, at least in terms of the variance, even though it is a kind of still have a periodic translation symmetry. Yes. Exactly, because Sx and Sz, they commute. And that be projecting Xz to some particular value does not change the eigenvalue property of Sx.
Then why do you need, I missed that.
Yeah. Oh, so yes, so practically, this is something will blow up, right? It's an infinite energy state. Because it's kind of like unbounded in energy, because it's a wave function everywhere in the phase space, and the total average excitation is infinity. And practically, we would like to have something bounded. Okay. And also, like, suppose, that's why, like, you want to prepare some bounded states. So it might be good to think in terms of stabilizer, which can stabilize a finite energy GKP state. And that's one way to write the stabilizer that stabilizes a finite energy GKP.
But it feels like that's already.
Yeah.
That's the same information. That means there's an envelope, right?
Exactly.
But the envelope has to do with the non-drug function, non-zero uncertainty of each of the blobs. The blobs have some structure.
Yes.
They have some spread. That's the width of the envelope. 1 over is the width of the envelope. So it's not a,
yes.
Not a,
yes, it's actually like there's a dual picture in there. So suppose we put in an envelope there with this to be 1 over delta. Yeah. Then the size of the blob is actually of delta, because that's kind of the requirement of uncertainty principle. Sort of like you need to have like a kind of a feature which is of order size delta. You need to have the complementary quadrature to be spread out at the order of 1 over delta.
But I thought we already have that, because each blob we talked about is coherent state, and you haven't even drawn that. Well,
this is because what I draw here is already a finite energy GKP state. Okay, if it's an infinite energy GKP state, these will be infinitely sharp peaks. Yeah.
So you just implicitly already.
That's right. Yeah. All right, good. So now maybe let's see. One of the feature is about, so far we mostly talk about how to stabilize and protect the information, and didn't talk much about how to process the information. And for GKP, it turns out that you can like do almost all the Clifford gates by using quadratic Hamiltonians, like a beam splitter, 2-mode squeezer, or like a phase rotation. But there is one key ingredient, which was actually recently people find, is that what you need for universal quantum computing is GKP plus vacuum, then plus kind of like the Gaussian operation. So because GKP plus Gaussian is not sufficient for universal computing, but what matters is actually, it turns out, even though we will think vacuum is trivial, but when you project vacuum to the GKP space, it turns out that actually gives you a magic state. And that is actually like I would say, gives a lot of excitement, because people say that, okay, everything we know this, how to do vacuum, probably Gaussian operations are more feasible. So all we need is just the one ingredient, which is the GKP states, even though it's highly non-trivial to prepare. But at least nowadays that people can demonstrate the GKP state prepared in microwave domain. Okay, so this claim about the universal computing with the GKP states is in this reference. That's 2019. So I think it's also exciting results to have. And also, in case people care about the fault tolerance threshold, suppose all the other operations are good, how much squeeze the GKP you need to have? Or maybe like what's the average photon number for the GKP? That's roughly need to about like a 10 dB squeezing for GKP, which roughly, I think about like 10-ish photons for the GKP states for average photon number GKP. Okay, So that's kind of give you a rough scale about how demand we need to have the GKP states. Yes.
Do you know how projective measuring vacuum is as Gauss?
Yeah, so what happened is that you have a vacuum state, and you need to measure the stabilizer for GKP. And how do you measure stabilizer for GKP? You use GKP to measure stabilizer for GKP. Okay, so suppose now here you can have a GKP, say the logical 0. Then one can perform some like C0-like operations, which you can do it with a quadratic Hamiltonian, and you measure this logical 0, measure the stabilizers associated with this Z direction. Then you can do another operation and then measure the X stabilizers, X. And based on these two measurements, you do some displacement of this original state, and you prepare that magic state. Yeah. Yeah, well, it's projecting vacuum to the GKP logical space. Yeah, and that turns out gives you the magic. Okay, it's not a perfect magic state, but it's good enough. Then you can do you can do magic state distillation to get almost perfect magic states. Yeah, but I think that's probably okay for people who really interested in fault tolerance quantum computing. Then that's kind of the latest progress. Yeah. So now maybe let's actually like have two more topics to go. One is about like a code optimization, which is this is about experimental implementation. That now we have these CAD codes, binomial codes, GKP codes. What I'm plotting here is a Wigner function of the code projection operator. Yes. Sorry, I didn't get the part which what do you mean by square root of p in that? Yeah. Yes. Yeah, so for GKP, it's a bit trickier to talk about distance. But if you wait for another 5 minutes, I'll talk about the comparison of the code. Okay, but before that, I just want to say, like, actually, since earlier, about 5 or 6 years ago, there's like actually experimental demonstration of these different codes. And here, just like as a fingerprint of different codes, we just plot the Wigner functions of these different projection of code space. And if you go to Yale, the coffee machine has these Wigner functions because Victor programmed the coffee machine there. So it's in there. That's maybe the only coffee machine with the Bosonic error correcting codes. Yeah. That's yeah. Well, this is the single mode encoding for a qubit using CAD code, binomial code, and GKP code. Yeah, and this is unique. Okay, so every Bosonic code, you will have a unique Wigner function for the projection of code space. And this is a nice representation because it avoids ambiguity of what's the logical 0, what's logical 1, because people are still arguing what's the best definition for that. But this avoids that issue. It's a projection that defines the two-dimensional subspace for the logical code width. Now, for the CAD code, you might remember we can prepare this horizontal or vertical type CAD. Here I slightly change the notation. In our notation, it's called plus logical and minus logical. And you can do the parity measurement non-destructively, so that if you do it frequently enough, every time there's a parity change, you know there's a photon loss. And for CAD code, you will find that there is this circle of life, like every 4 photon loss, it goes back to the original states, up to a slight change of the amplitude. So basically, if you can count how many photon loss modulo 4, you know how to interpret what's the encoded states that's left behind. So, and the comparison between Bosonic codes, in order to claim that error correction actually helps, what we need to do is to compare the error correction scheme with the best scheme that you don't do error correction for the same physical platform. So now, if we consider Bosonic codes with CAD code, if we have a good oscillator, the best scheme without error correction in the presence of loss error is to use a minimum number of excitations, which is 0 and 1 for one logical qubit. But no error correction, because there's no way to do error correction for this code. But this has a lifetime, which is the vertical axis is the process fidelity for quantum memory. The horizontal axis is the waiting time for your quantum memory. So that gives you about a lifetime about 300 microseconds. But now if you do error correction with a CAD code, it turns out that actually, even though the starting point is a bit lower, it's because the code encoding, decoding, they introduce some errors. But the effective lifetime is actually slightly better, a little bit over 300 microseconds. Yes?
How do you estimate the lifetime from these sort of data?
Well, you try to fit this with an exponential decay curve. Yeah, but here you see it does like a slowly kind of, it decays a bit slower compared to the other one. Yeah, but this is not the only experiment. This was kind of done like the first one in 2016. And earlier this year, there are 2 more experiments. Now we kind of complete the full sets with the binomial code and GKP code. And you see that this is the improvement factor by taking the ratio between the error corrected lifetime versus the best lifetime without error correction. And you see it go from like maybe a 10% improvement to this 130% improvement for the GKP code. Okay, so here there are the references, and there are different details about how you implement different error correction. But here I want to convey the message that yes, it's actually real that people are doing error correcting code and see the improvements with the Bosonic codes. Yes.
Isn't it a little arbitrary for the 0-1 encoding?
Good point. We actually did the optimization, use a semi-definite program to confirm it is actually the best code you can do. Yeah. Yes.
What about the overhead?
Excellent question. If you look at the data points here, the horizontal axis indicates it's about like every 15 microseconds we do the error correction. In principle, experimentally, we can do it every 1 microsecond, but we don't do it that way. It's because every time we do error correction, we introduce a few % error. And it's a trade-off that you want to probably correct more errors than the errors that you introduce. So that's why we wait a little bit longer. And also that's actually the challenge also, maybe I mentioned in the last lecture, that how can we do it fault tolerantly? Because that few % error is mostly due to the ancillar transmon is not perfect. So while you're doing the error correction, extracting the parity, the transmon decayed with 1 or 2% chance. So that will mess up the system. Okay, and that's actually the open challenge. Like, okay, can we do it more fault tolerantly using the kind of like some fault tolerant or error transparent design? Yeah. Okay, good. So now let's actually come back to the question about the comparison of different codes. Because when you see there are 3 different choices of code words to correct loss errors, one natural question is, which one is a better code to correct loss errors? Or which one can correct most of the loss errors as we can? So now we have 3, CAT, binomial, GKP. And well, if you have a preference, so who thinks the CAT will do the best? Or who likes the binomial code, like thinks that will do the best? Or who thinks the GKP will do actually the best performance? Yeah. Well, actually, it doesn't matter because it depends on the parameter region that you choose. Okay. but there are like most of the parameter region. It turns out that there is a code that can perform better than the rest. So in order for comparison, we first need to set a standard. Say, what is the figure of merit when we compare different codes? And that figure of merit, what we call it, is called the entanglement fidelity. So when you consider the performance of encoding, there's always ambiguity about which is the code word that you should plug in to see how good it is, right? One way to do it is to sample over all possible code words. And the other way to avoid that is to put some states which is maximally entangled with the ancillar. So you have a logical qubit maximally entangled with a 2-level system, which is assumed to be idling but perfect. So you start from this maximum entangled state, phi, and put half of it through the qubits and go through this encoding noisy bosonic channel. Then you do the optimized decoding, and then you combine with the reference system and see how good that state is compared with the original input. So that is output state, and ideally it should be the same maximum entangled state that you put in. And the one way to compare how close it is to compute this entanglement fidelity. So this is output sandwiched by the original input. And that gives you this definition of entanglement fidelity. And we consider a special case of entanglement fidelity where the psi is the maximum entangled state to put in, which is a Bell state for the case of qubits. And pose a constraint that the average photon number for the code is no larger than some maximum photon number. And we choose it to be like some number like 10. And then actually optimize the recovery via semi-definite program. Okay. And yeah, this is actually like Victor did that like a few years ago. And this is the comparison. So horizontal axis, we call it gamma, which is the photon loss rate. So every photon will have, say, like a 10% loss if this is the point. And the vertical axis is the entanglement fidelity introduced earlier. And you see that generally the higher the better. So you see that this GKP or the GKPS, because there are different variations of GKP. Let's tentatively not worry about it. That overall outperform the cat and binomial code for a wide range of parameters. Okay, but if you're looking further in here, actually there will be the cat code, binomial code in principle can outperform GKP if the error is really, really small. It's because, especially the binomial code, it's an exact error correcting code for certain loss errors. So it guarantees to suppress error to second or higher order, but the GKP is approximated error correction, so there is no such guarantee. But for the relevant parameter region, let's say 0.5% to like a 10%, this is the log plot of the infidelity. And you see that the GKP decays much faster compared to the cat and binomial. And if you look at these, the numbers here, with 10% loss, the GKP with average 10 photon encoding, it can suppress error to 10 to minus 4. Okay, that's like you have a fidelity of 99.99% fidelity, if even with 10% loss. Yes.
Can you remind me what is this optimization being done over?
Yeah, so the optimization is actually optimized over the recovery channel. So in order for a fair comparison, I already have a fixed code, fixed noisy channel. I want to get the best performance of my code in order for comparison. And it turns out that there is this procedure using semi-definite program to get the optimal recovery to compute for our qubits. The only issue is that optimization has a complexity of a Hilbert space dimension to the 8th power polynomial with dimension, but it works for Bosonic case because we only have like about like 10 to 100 levels. But when you do the qubits, that's a bit tricky because it's a 2 to the n, right? So that becomes very quickly growing to be very large. Yeah.
Is it well known that the entanglement fidelity is convex with primers?
So for this case, we actually know this is a linear dependence on the recovery or the encoding. Okay. Yeah, because the definition of this entanglement fidelity we choose.
For internal parameters,
yeah.
Non-linear function.
Yeah, but yes, that's true. But if we think this as a super operator, it will be still a linear function on it. Yeah. So that actually helps to get this good solution. Okay. Yeah. Question. Yeah.
So this data is all experimental.
Well, it will be nice. I wish it could be experimental because we could get to 10 to minus 6. Yeah. So this is theory, and also with the assumption that we have a perfect encoding, perfect decoding. Yeah. But I think that maybe experimentally they probably like have maybe 10% loss with maybe like a 90% plus like a fidelity because they're just kind of this like a little bit above the break even still. Yeah. Yes. X-axis is called the loss rate, which is suppose it goes to a beam splitter with 10% loss, like that. Yeah. Yes. Yeah. Yes. Okay. We haven't looked into that, but what we did is actually is exactly along your direction. Is that you may notice that there is this symmetry between encoding and decoding, right? It's just whether you multiply this first or multiply that, right? So one scheme, so far we kind of like, when we compare different codes with some fixed code in mind, we only optimize the decoding. But what about encoding? Can we optimize that too? So one way to do it is we fix the decoding and optimize the encoding. And we can alternating the procedure, repeated many times. And it turns out that there is actually something kind of very nice that actually like Kunju come up with that after taking this convex optimization class. And that's kind of like one of the outcome from that is that you start from random code. You optimize the encoding, optimize the decoding, optimize the encoding. After one round, it looks still pretty random. But after a few hundred rounds, you start to see this hexagonal lattice pattern to emerge. And they basically converges to the same solution up to some gauge degree of freedom, which is the overall phase rotation, because that's essentially the same code up to some general phase rotation. And it reminds us of efficient packing in 2D because the hexagonal lattice is the most efficient packing. Okay, yes. What is? So the random code is just pick some projection operator with rank 2. It choose a two-dimensional subspace. And you choose different random codes. It turns out it all converges to the same solution or same family of codes, the GKP code. So that gives us the kind of numerical evidence that the GKP code seems to be emerges as an optimum coding, and the particular GKP is a hexagonal lattice GKP. That actually gives us a better, more efficient packing. Okay, and there's some analogy, and also there is like a good loss rate with a good performance. And actually, if here we constrain photon number to be 3 or 10, but if we increase the photon number, it turns out that the performance can be even better. We can get 6 nines if with 10% photon loss with 100 photon average GKP code. Yes. Yeah, optimize the decoding, optimize encoding. That's called one iteration. And they repeat it a few hundred times. A nice solution emerges. Yeah. Yes. Yes, 10% loss. Yeah, that's true, because here, like I would say the loss maybe need to be less than about like a 30 or 40% loss. Then GKP does better. And when the loss is pretty high, maybe it's better to do 0-1 encoding. Yeah. And when it's larger than 50%, there is no way you can preserve the information. Yeah. Yes. Yes. So good question. And so practically, it's actually very resource consuming to do this like SDP, and especially want to iterate a few hundred times. So that's why M bar is a bit smaller. But now we actually like there's some like ongoing process that actually some of my students figure out that you can sort of skip the SDP and just use a particular recovery channel called transpose recovery, which guarantee you'll get close to optimum solution up to a factor of 2 in the infidelity. And then that you can get analytical calculations based on the error correction matrix. So that can be much kind of more efficient, and they actually push that to about 100 photons average GKP. And that's why we can push this with a 6 nines. But there is a fundamental limit about what best you can do. And that limit for the square lattice GKP, that's like a 1/. So that's kind of the infidelity. So this is for square GKP. And this expression is actually very impressive. I want to kind of say a few more words about this, because first of all, when gamma approaches 0, it's e to the minus infinity, which is indicating the infidelity goes to 0. Okay. However, when this gamma is 0.1, so this is say like for gamma is 0.1, this becomes e to the minus pi over 2 times 10. This is a very, very, it's a e to the minus 6-ish, right? No, it's e to the minus 12 or 15-ish. Yeah, it's 15 or 16. So this is actually like a really, really small number. Okay. And that's why actually And also this function is not analytically continuous when you actually push the gamma to be 0. It quickly goes to like a 0 when you have a small gamma. That indicating that you can actually have a very good efficient coding. Okay, yeah. Yeah, that's actually the expression for infinite energy GKP. And it's a bit surprising that actually like when you increase the photon number, it's actually getting better and better. And which is different for cat code and binomial code, which had the optimum choice of photon number. And the explanation is that one way to think of it is that if you have a loss and amplification channel, you can get a more sharper points when you do that correction with a larger size GKP, so you suffer less of those initial random noise. But the optimum scheme, this is actually like it's still a bit non-trivial, like what exactly is the recovery procedure that one need to do? Okay, yeah. So that's a open research question. And also like, even though here the GKP is gives you the best performance for a wide parameter range, it doesn't mean we have to use GKP. Okay, it depends on like really the complexity of implementation, because maybe some other codes like cat codes, you can autonomously stabilize it. And also depend on the purpose of the error correction, as if I have time to, at the end, talk about the error correction for sensing, then it turns out the binomial code has some extra advantage if you want to use error correction for sensing. Okay, yes. And so it depends on what you want to use it for, right? Ideally, if I don't constrain by the energy, I would prefer delta to be infinite, to be 0. So I have infinite GKP with the best recovery. But to some point, I sort of get diminishing return because my delta is small enough, it's already almost as good as the best code you can get. Yeah. So typically, I think when delta becomes, delta square becomes 1 over gamma, sorry, it's a delta square becomes comparable to gamma. I think that's already sufficiently small. Yeah. So we mostly talk about kind of the discrete error correction, like by discretized evolution, syndrome measurement, correction, feedback, and then repeat procedure. But in practice, there's also advantage to do error correction continuously. Like I mentioned for the cat code, you can design and engineer a Lindbladian jump operator to stabilize it. And for GKP, there's something kind of similar, but still kind of more like a Trotter-ish like procedure to approach that. But there people are thinking more of those error correcting codes. And also for the pair cat code, I briefly mentioned, you can actually autonomously correcting both loss and dephasing errors. So I think these are actually like very promising approaches. And also sometimes it will be good to introduce both Hamiltonian and engineer dissipation. And like a Kerr-cat is also another way to use a Hamiltonian, so that the ground state manifold has a twofold degeneracy, which is exactly the cat code. Now, the key feature for these two platforms is that people identified that you can do something called the bias preserving feature, is that once you have a good separation of code space in your phase space, then you will be able to inhibit certain errors so that the other remaining error can be more efficiently corrected using the next level of error correction. Okay, so that probably all I want to talk about the Bosonic codes, and I want to talk about something beyond just using Bosonic error correction for the next 35 minutes. But before that, if you have any questions, I'll be happy to answer about the Bosonic codes. Yes. So what theorem? Yeah. Yeah. So, well, I think that the current approach is basically we get some effective logical qubits at the Bosonic level, either biased or different some error models. Then we use surface code or LDPC code or some other codes to get the threshold. Okay. And I think there are some potential improvements, like basically when you get the syndrome information for Bosonic codes, you actually get analog information, for example, like GKP code. And that information can pass on to the next level, so that maybe the next level you can do maximum likelihood decoder to improve the performance. And indeed, we find those cases with the GKP concatenated with the quantum LDPC code. You can use it for quantum communication and correct more loss errors. Yeah, so that's kind of like something that maybe implies there may be a better way to integrate the Bosonic codes with the higher level codes. Yes. Yes, great. So there are like different ways to do two logical qubit gates. And one is, for example, the GKP, you can do it like a beam splitter two-mode squeezing. And for the generic bosonic codes, there is a way to do two logical qubit gates. It's called the exponential swap gate. So I will just write the exponential of the swap times angle theta. So swap here literally means you exchange the two modes. Okay, it's a Hermitian operator. So I can exponentiate it and get this exponential swap gate. So if you're familiar with the spins, usually the swap is just the sigma dot sigma kind of the exchange coupling. And people know, like earlier in the early 2000s, that just to use exchange coupling with a good choice of encoding, then you can actually do the universal computing for the defined logical space. It turns out if we can do exponential swap, we can do the similar thing, because this, okay, here is the swap over the two bosonic modes. And then you can achieve that by putting whatever logical state 1 and the logical state 2. By doing this exponential swap, it guarantees this will become kind of a psi 1, psi 2 with some like a superposition, psi 2, psi 1. With the cosine theta, sine theta, maybe with an I. So it guarantees stay in the code space. And just by doing this, you can show it can do a universal computing as well. Okay, so that's kind of like a, how to say, a way a little bit cheating, just say it works for all bosonic codes. Okay, but practically, you may ask how we do such an exponential swap. And the idea is actually the following. We know how to do identity operation for bosonic B1, B2. We also know how to do like a swap operation by implementing a Mach-Zehnder interferometer. So here I can have a phase shift theta. So I have B1 coming in, B1, B2 coming in, and B1 prime, B2 prime. So each of these are 50-50 beam splitter. And you might remember from your optics class, when this theta equal to 0, then the interferometer probably this certain way, say B1 go to B1 prime, B2 go to B2 prime. When theta is pi, it's swapped, right? And the way to do exponential swap is to introduce this controlled rotation angle, and I can put in some quantum states here so that I will do this control rotation, and I can, let me see. Okay, basically here I need to do this, the phase rotation that's controlled by this qubit. So I know that I have identity plus, so the exponential swap is cosine theta identity plus I sine theta swap. So I want to design the circuit that implements cosine identity and implements I swap based on this controlled phase angle theta. And that can be achieved by putting some like ancillar states here. And I think in the end, there's some way to trace out the ancillar, and at the end, you'll get to this exponential swap. Okay, sorry, I forgot about the details. If I remember correctly, I think that this part you can measure the ancillar in some basis, and it will give you the swap. But okay, I need to look it up. But this is actually an experimental demonstration in Robert Shulkov's group. They demonstrate you can do exponential swap between the two bosonic modes. And that will allow you to do universal computation. Yeah. Yes. Yeah, you can have a microwave with two tones coming in, and you drive with a pump at the frequency difference of the two modes. Well, I think there's no reason you cannot do in free space, but I think right now it's it's better you have a confined kind of localized modes. Yeah. Yes.
Kind of maybe more general question. How do you measure the stabilizer?
For which code?
Well, let's say this one.
For the GKP. Yes. Well, there are actually like different ways that you can measure. So the ideal case is actually I have some ideal GKP states. So I have some logical states with some error acting on it, right? And then I have some perfect GKP, say logical zero state. What I can do is say logical plus state, I do a CNOT gate here. Because it's a logical plus, it commutes with a CNOT, right? So there should be no effect acting on the original state. Now, what happened is, now this time, I can actually perform a stabilizer measurement of, I think, SX. So, or alternatively, I can just do the harmonic measurement to measure what's the value of X for my bosonic mode here. So why this is okay? Because I cannot do this X measurement over the original logical state, but I can do it with this ancilla. It's because measuring this X does not tell me what's the original X in this code word, because my ancilla have this X positions as a superposition. So this X is actually the ancilla X plus this original code word X. So, but I know the ancilla is perfectly prepared in some discrete lattice. So if there's any deviation from the discrete lattice, it has to come from the code word. And that is where I can know what the value is and the feedback, making some displacement along X. And that's a way to correct random displacement along the X direction. And similarly, you can do a similar circuit with this GKP 0 logical and measure SZ and the feedback with some displacement along the momentum direction to correct the other quadrature error. And that's kind of like the ideal circuit design if you have perfect GKP as the ancilla.
It's because of C0 you measure the sum.
Yes. So what's a C0 here? So C0 is actually, it's an exponential of, let me see, I want the X to become, so it's X1 times P2 with a displacement of some coefficients with some constant in the front. So any position of the X1 of the first mode will be mapped as a displacement along the P2, along the X2 direction, because that's what the P refers to. So it will map the X outcome for this output to be X ancilla, which is plus X code word. Yeah. So maybe let me just write, this is the code and this is ancilla. Yeah.
What's the word under that?
Okay, yeah. Let me write it again. So it's lambda times X X code and times the P ancilla. So this is the code that you want to do error correction, and this is the ancilla that you introduce. So it's a quadratic Hamiltonian that can map the position information to both here, and you measure the position, you can infer the error. While at the same time, there is no back action to the original code word, because the lattice here matches with the lattice there, so that when you add up those lattices, it still gives you the original sets of lattices. Yeah. So yeah, people, I think that this is okay. In theory, it says quadratic, but practically it's also a bit non-trivial because it involving two-mode squeezing as well. Yeah.
That coefficient X is sorry, that coefficient, that's the square root of pi.
Yeah, I think that maybe you want to choose to be 1. I think 1 is already enough.
X
Yeah.
code on the lattice.
Yeah.
Then it just add operators 1 and just give you 1.
That's right.
Then
Yeah. Exactly. So this is
different square root of pi.
yeah. Yeah. So basically, you have X code and P code and X ancilla and P ancilla. And this gets mapped to X code, and X ancilla becomes X ancilla plus X code. And the P code gets to P code minus P ancilla, and the P ancilla is unchanged. That's what this unitary map does over this the code word. And what we're using is this feature with a perfect ancilla that try to measure the deviation from the code. Yeah.
But basically, how is that operated?
So experimentally, what they do, there's another story, is that they actually use a two-level system to measure the syndrome. So if you have your GKP code word, now let's have a two-level system. I let them evolve under a Hamiltonian, and that unitary will give me e to the I, and let's say I want to measure the partition operator for the code with a kind of a excited states E. And now this has a square root of pi, so I multiply this with the square root of pi for that. So what happened is that if the code word is in the lattice, then that multiplied by the square root of pi, and it will give me this quantity will become the trivial one, which is 2 pi. Okay. However, if there's a deviation, then what happened is that ideally this will implement identity, but practically there will be some like e to the I delta phase times the excited state, which will prepare my symmetric superposition to some slightly component with anti-symmetric superposition. When I measure this, I will know whether it's a plus or minus. And if I measure something like a minus, that's indicating there is some deviation in my position. However, this measurement only gives me one classical bit of information, the slight displacement. So it is an incomplete measurement called a weak measurement. And with a weak measurement, you sort of like you need to update your description of the GKP code with a modified distribution of what the displacement may be. And you can even feed back with some small displacement to correct those errors. You don't make dramatic changes, you do small displacement. And by repeating it multiple times, you actually do weak measurement and feedback that can help you to also stabilize that operation. Yeah, you do it many times. And you can think that this procedure is something also related to earlier I talked about the kind of you want to stabilize to the envelope function. So what they did is they not only measure one quadrature, they also measure the other quadrature, do some other feedback that effectively implementing the stabilizer operator with a finite energy GKP. Yeah, because that's kind of a, how to say, a poor man's version, just use a two-level system to get something wrong with weak measurement. Yeah. Okay, so maybe I think for the remaining time, I want to talk about something which is beyond the Bosonic codes, which is about like, we use error correction, mostly thinking in the context of quantum computing. But I want to point out there are two other applications, at least, for quantum error correction. So one is actually for quantum communication, because it's very natural to think we send quantum information using wave packets over the fiber, which is a Bosonic mode. And for Bosonic modes, for the fiber, the dominant error is excitation loss error. And how do we overcome the excitation loss error? Well, we have to kind of like divide and conquer, because if you send the information directly over the fiber over 1,000 kilometers, basically there's no signal left, okay? So you have to kind of cut the entire quantum channel into smaller sections connected by quantum repeaters. So in our classical communication, we also do similar thing. We send a classical signal, our classical repeater will amplify the signal and then send to the next station. That's how this under ocean cable, how they worked. The difference is for quantum case, we cannot just amplify the quantum signal. There is no cloning theorem, okay? So what we can do is actually we can do error correction. We can encode the information which is robust against loss errors. And going through the fiber, suppose it's 10% loss overall, then we can do our GKP code to restore it with a fidelity 99.999. And then we can send it over the channel again, right? If everything goes well, we can send it over really long distance. So natural question is, what's the maximum amount of information you can transmit over a lossy fiber? And how to design error correcting codes to approach it. Okay, and this set of questions has been kind of like addressed in the classical communication over the past centuries. Kind of like in the 40s, last century, people talk about like a channel capacity, which Shannon derived it. And took people about half a century to design these good codes. So nowadays we're using classical LDPC code and polar code for our 5G network, which essentially approach the channel capacity. In the quantum case, I think the situation is similar. Like in the late 90s, that people talk about the quantum channel capacity. And there are certain cases that we know the channel capacity, and there are many cases we don't know what the channel capacity is. So that's an interesting open question. If you're interested in quantum information theory, that's one of the most outstanding questions. And the other is actually designing codes. We can design with a discrete variable or continuous variable. And since the fiber channel is naturally a bosonic channel, I would say for communication, it will be good to look into these bosonic codes. So there are actually like a progress along this direction. So here is actually a plot in terms of the channel capacity, which is the maximum amount of information you can encode in terms of number of qubits per mode. The horizontal axis is the loss probability, which is every photon, what's the probability it will be lost during the transmission through this lossy channel. This red and the blue curve actually corresponds to the overlap, because for this particular channel, we know exactly what the channel capacity is. And for this lossy channel, with eta being the transmission, this function, the channel capacity is log eta over 1 minus eta. So you can convince yourself this is the right formula, because when eta is 50%, this is a log over 1, log 1, which is 0. So the channel capacity vanishes at the 50% transmission, which is consistent with the non-cloning theorem, right? Because otherwise the environment will get more than what you do. And for a typical case, you will not be able to, it will violate no cloning. However, that's the performance of the GKP code. If we do multi-mode GKP, optimize the lattice spacing, gives us the efficient packing in the higher dimensional space. And that's kind of the performance we can get for the last channel. And this was a result we get like about 5 years ago. And the latest unpublished result is actually, we find with optimized recovery, like transpose, we can push this line almost overlapping the other curve. So now we can probably will have, maybe stay tuned in the next few months, we might have a paper claiming that we have a channel capacity achieving a GKP code. And for more other channels, there could be thermal noise channel, then it's still also like there's an open question about what's the channel capacity. And maybe developing better code can help us to improve the lower bound. And hopefully we can maybe close the gap between the lower bound and upper bound. So this is for the, I think for the context of quantum communication. Now the figure of merit is not just the fidelity, it's actually the channel capacity about your choice of the code. Now, in the last 15 minutes, I'll talk about using error correcting codes for another application, which is quantum sensing. Okay, because in some sense, quantum sensing is probably like maybe people are already using it and taking the quantum advantage for quantum sensors. For example, the gravitational wave detectors, the advanced LIGO, they're actually already using the squeeze light to enhance the sensitivity. So now the question is, actually, can we actually come up with something that error correction could help with quantum sensing? And this was kind of like about 2 years ago, happening roughly the same time the LIGO detects the first gravitational wave events. And also like there is a demonstration that the error correction, we can go about break even. So the natural question is, can we actually come up with a good error correcting code that can help us with quantum metrology? Okay, so maybe one first impression is, okay, well, you already use error correcting codes for quantum computing. Should it be natural that we can use error correction code for quantum sensing? Right, and which one is easier? Is it easier to use error correcting codes for sensing, or it's easier to use error correcting codes for metrology? And I think the answer depends. Also, like for sensing, one of the difference between sensing and the computing is that when you're sensing, you have a particular signal you want to sense. And that signal is associated with a particular Hamiltonian evolution. At the same time, there may be noise. And when you want to do error correction against the noise, you need to make sure you don't correct the signal. Okay, so you have some restricted choice of the code space that will be sensitive to the signal, but hopefully will be correctable against the noise. And that is the additional condition we need for quantum error correction for sensing, which is different from computation, because computation, you can always come up with clever ways to do encoding. As long as you correct the noise, you can introduce your own sets of logical operations to achieve the computation task. But for sensing, you have a constraint. You need to sense a particular signal, which may or may not be distinguishable from the noise. Okay, so maybe just maybe a setting a bit stage for sensing is, well, maybe let me ask, how many people know about the Heisenberg scaling for quantum metrology? Okay, good. I hope some of you will learn something from this lecture. It's because I think it's depend on different audience. That for AMO audience, that's kind of they do for atomic clocks. But I think that here, one question is, okay, what can we do with the quantum sensors, right? What's the best sensor you can do, and also what's the fundamental limit? So how do we use atomic clock to measure the time very precisely? So simple model is kind of our sensor or even magnetometer to measure magnetic field. It's just to think about you have a spin, say electronic spin, which has spin up or spin down, which has energy splitting for different magnetic field. And energy splitting here, I'll call it the omega, which is proportional to the magnetic field signal. Okay, and now we want to measure omega. Okay, one way to do it is let's prepare the spin in the 0 and 1 state, which have different energy dependence, different eigenenergy, and they will evolve from a symmetric superposition to some combinations of symmetric and antisymmetric superposition. Okay, so what you do with the Ramsey interferometer, this is you prepare some superposition and you let it evolve under the Hamiltonian, and you measure what's the overlap with the initial state that you prepare. If omega is 0, you will measure the initial state 100% of the time. But with the finite omega, you will see this oscillatory pattern that overlap with the initial state. Okay, and now if you have a rough estimate what the omega is, but you want to know precisely what they are, you could wait for some time and measure this probability distribution, and from which you can infer what's the value of omega around that neighborhood. And the precision you can get for the delta omega scale inversely with the interrogation time that you apply for the system. So if you have, here we assume we have a perfect coherent quantum sensor, so you can let this evolution time to be t to be as long as you want. Then you will be able to sense the small deviation of your signal inversely proportional to the total interrogation time. And this inverse with time is called the Heisenberg scaling. Okay, it might seem natural that, okay, it's scale inversely with time because that's a dimensional analysis. That's what you get. Okay, however, this is actually non-trivial because think about when you do the undergrad physics lab, you need to measure some distance very precisely. You do it 10 times, you improve the precision by 1/√10. You do it 100 times, you only improve it by kind of like a square root of n, the repetitions that you did. It's because of those like the central limit theorem with that kind of how you converge. That's actually the variance. The standard deviation is actually reduced by square root of n when you measure repeat n times. And that's the classical scaling we get. And now, if you classically, you may repeat it many times, but the number of repetitions scale linearly with time, and the precision will scale only square root with the repetition, and hence only square root with the total time of your classical measurements. So that's the difference, whether it's linear inverse or it's a square root inverse. Yes? Yeah. Okay, how you get the linear scaling? So suppose I already have a rough estimate of what omega is. I look at the neighborhood, and if I fix the total time, then if I change my omega by say like 10% or 1%, then basically my signal, the probability distribution will also change about 10%. Now, if I increase the time by a factor of 100, that 10% will be, okay, maybe that's a bad analogy, by a factor of 2, that 10% will become 20%. You will actually see that big change in the in the probability distribution, which tells you that the sensitivity to the change of omega is inversely with the total interrogation time. Yeah, it's just because it's a product of omega times t. Yeah, and notice the reason that you get this quantum scaling is because it's a coherent unitary evolution, and the probability amplitudes actually add up coherently. Okay, if we have a decoherence, then what happened is the evolution will no longer be a pure state. You have a mixed state with off-diagonal terms decreasing, and the decreasing of off-diagonal term depends on the dephasing or bit flip rate. And then the extreme case is these terms disappear, then you will no longer see any difference because whatever what you measure, it's a 50% chance that you'll get. It's a mixed state. But for finite time, you will see this exponential decay envelope of your signal. So this is, once you have such an exponential decay envelope, you get to diminishing return region if you get to really, really wait for a long time because you actually don't see the signal. It's better to choose a time which is comparable to the decay rates and get the signal and repeat the experiment many times. Now, again, you have a characteristic time scale for the repetition of the experiment. Then once you repeat it many times, it becomes, again, the classical averaging of your measurement signal. And that will suffer the 1 over square root of n because of the central limit theorem. It's the variance scales inversely with n, and the standard deviation scales inversely with the square root of n. So that's why we actually, decoherence typically will prevent you from achieve Heisenberg scaling. Okay, so this is kind of like typically what people know about the quantum sensor and the precision measurement. Now the question is, can we use error correction to help to suppress the noise and restore the quantum scaling, which is the Heisenberg scaling for sensor sensitivity? Okay, yes.
So if it's perfect coherent, I should just think of it n as 1, but I don't do it many times.
Yeah, if you can really do the quantum case, you probably really wait for a longer time. And also, if you really want to know the value of the phase, you can actually do quantum phase estimation algorithm to measure that quantity like a bitwise to know the value. Yeah. So, but if you have decoherence, there is a certain limit about the precision you can measure, and it becomes very, very expensive if you want to kind of know more precisely about the precision.
Total time divided by
That's right, for this noisy case.
independent possible.
That's right. Exactly. Yes. So now the idea is actually we want to use error correction, hopefully to encode our sensor as a logical state, which will be sensitive to the signal, but at the same time, we can also do error correction to correct the noise. And if that's possible, then we can claim at the logical level, it will be a coherent evolution because we do error correction against the noise so that we can effectively have a coherent evolution sensitive to signal in the logical space. Then we will be able to restore the Heisenberg scaling. Okay, but yes, 5 minutes, yeah. But otherwise, if we cannot do that, then we will not be able to achieve a Heisenberg scale. Okay, yeah. So now let me, just the setting is that we can think about the most detrimental noise, the white noise described by this Lindblad master equation. And you have those noise jump operator, and for small time evolution, you can think there is the ideal evolution, but there will be some like a noisy evolution that branches out from what you want. But hopefully we can do some like encoding and do interrogation, error correction, interrogation, error correction, alternating the procedure. Finally, we do the measurement, and hopefully the error correction will suppress the error to high order while we still maintain the sensitivity to the signal so that we can get the favorable sensing. And instead of going through all the detailed proofs, here is the result, which I think, and let me explain what that is. So it's a necessary sufficient condition whether error correction can give you Heisenberg scaling with for sensing. So the condition is depending on that how bad the noise is, okay? Because the right-hand side I call the Lindblad span is basically an operator space spanned by Lindbladians. It's Hermitian conjugate and the product. And those are actually the operator space which are contaminated by our Lindblad, by our quantum noise process. You can think when you write the Limblad master equation, it will be natural to think that you will write these L or L daggers acting on different sides of the density matrix. And they stopped at the quadratic order. And those are the contaminated operator space. And then on the left-hand side, the G is a generator for the Hamiltonian, which are the good operators we want to have. And the question is, if the good operator is not within the contaminated operator space, then we will have some residual part which is not contaminated, and we can just sense that residual part, which is orthogonal to the Limblad span. And we can design error correcting codes that are only sensitive to that orthogonal part while correcting the remaining noisy operators from those Limblad span. So that's kind of a constructive way to say it. And let's look at the example. Suppose I have a two-level system. I want to sense the energy difference, but I have bit flip error, poly X. So what's the Limblad span of poly X? It's identity, poly X square. But poly X square is identity. So the Limblad span is identity and poly X. Now the signal is poly Z. And can I write a poly Z as a linear combination of identity and poly X? No, we cannot, right? Because the operators, we know in terms of trace products, they are kind of orthogonal. So therefore, the poly Z is not in this Limblad span, and we can come up with error correcting codes to sense such a signal. And that choice of code is actually very simple. You just prepare the 0 probe and the 0 ancilla, and only probe suffer the noise, and ancilla in our setting assumed to be perfect. You can do 1 probe, 1 ancilla. So this is a logical 0. That's a logical 1. So if there's no bit flip, I can maintain the superposition of these states to sense the signal. And if there is a bit flip, what I should do is I should keep monitoring if the ancilla and the probe, they are consistent in terms of this measurement basis. If the product of Z of the probe and product of Z of, with Z of ancilla become -1, I should immediately flip my probe because there is a bit flip acting on the probe. And that will restore to the logical space so that you will maintain the coherence of the evolution for your sensor. So that's why actually this would be the code word that help us to correct the bit flip error. Now we can, if you have a dephasing error, you can show there's no way you can actually to do that because you cannot differentiate whether it's part dephasing or from the noise or phase signal that you try to measure. And you can prove it by necessary condition by quantum Fisher information, which if you're interested, you can look into the references how to do that. And the sufficient condition is to construct the error correcting codes that help to do it. Okay, so I think for the time constraint, I'll probably just leave it there. Actually, the proof was proved by Sister Joe, a former student in the group. You can come up with the code word design for the C0, C1, and then that will give you the sensitivity to signal while correcting errors. So I think that's probably maybe related to Bosonic code. Here is one story that if you want to sense the frequency shift of the Bosonic mode with the presence of loss noise, you cannot do that because if you have a loss error, A, and you can come up with A dagger and A dagger A. And that form the Limblad span, which covers the signal, which is A dagger A that you want to sense. So therefore, according to the theorem, it's a no-go. You cannot restore Heisenberg scaling, even if you can do error correction. And we can twist the definition, say, what if the signal we want to sense is a Kerr effect, A dagger A square? Then the A dagger A square is not in the Limblad span because it's a quadratic in terms of A and A dagger, while the Limblad span is up to quadratic. So we can come up with the error correcting code. And the solution is something like a binomial code which shows its use. That you can say n equal to 2, so this n equal to 4. So the code word C0 is a 2-photon Fock state, and C1 is the superposition of 0 and 4. And these two code words will have a same average photon number, but the photon number variance, the n square, they will be different because n square here is 2, and n square here, the average is 8. So they have different variance. So the logical evolution will depending on whether it's logical 0 or logical 1. And the evolution will proportional to the Kerr effect that you try to sense. While at the same time, we know binomial code can correct photon loss error. So you can correct loss error while performing sensing for the phase, for the Kerr effect. Okay, so basically, there's some other extensions, which I will leave you there. But here, one message I want to convey is there's actually a connection for error correction to many other quantum applications. For example, for quantum metrology, we know that we want to improve sensitivity. And there is upper bound called the quantum Fisher information, say that's the best you can do. But the schemes with error correction can give us better lower bounds. And the hope is that maybe we can get better lower bounds and improve tighter upper bounds, and they will converge. And sort of we know, get some results in terms of the Heisenberg scaling for those. And you can also extend that to like a quantum communication, because for quantum communication, the upper bound is the quantum channel capacity, while the lower bound is the design of error correcting codes to achieve that capacity. So in that sense, it's a very similar story, except in a slightly different context. So finally, just as a summary, we can talk about the error correcting codes and maybe applications for kind of like a co-designed code for applications of quantum communication and quantum sensing. So I would say like maybe the key message is when we design the codes, we need to think about what's the physical platform, what's the dominant error, and how can we implement those error corrections. On the other hand, we should think about what do we want to use for the error correcting for, either for computing or communication or sensing or other applications. And that actually will help us to design a good code. Okay, yeah, thank you for listening.
In the quantum sensing thing, like in the atomic experiment, what we suppress the error is not to use Ramsey, but fixed variances, dynamic decoupling.
Yes.
Then we suppress like from T to or vice versa.
Yes.
Is it related to that?
Well, yeah, actually, it's related to the model that we assume for the error. Because here we assume the error model is a Lindbladian master equation, which is a white noise, no temporal correlation. But I think typically the dynamical decoupling assumes there's a strong temporal correlation for the noise so that you can use echo to cancel the noise while maybe maintain the alternating signal you want to sense. Yeah, so if you know the structure of the noise, you should, before you do error correction, that's actually, you should think other ways if you can do it to suppress as much as you can. Because I would say error correction may be more like the last resort, right? If the other scheme doesn't work, then you have to do the error correction to take away the entropy. Because if you know it's just an unknown evolution of Hamiltonian, it's actually a unitary evolution. And you may want to think about other ways to kind of design the coherent evolution rather than kind of using the kind of the last resort of error correction to correct those errors. Yeah. Yes. 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 So that's a maybe. And there are two ways of saying the Heisenberg scaling. One is with the total integration time. The other is with the size of the system. And both will be inverse with the time or with the inverse of the system. But for that GHD scaling, it's actually assuming you don't have decoherence, it will give you inverse scaling with n, right? And if you have dephasing, that would not work, right? And on the other hand, you may say, well, if you have a bit flip, but you have it encoded in GHD states, and can you measure those things and correct the bit flip error and still maintain the scaling? I think for that special case, yes. Yeah. Good.